Okay, we are moving into the next chapter. It's called carbon. It's basically carbon and climate. Obviously, the tremendous interest and the daily barrage of news about climate is related to carbon and other greenhouse gases. And we are just coming out of COP26, which made a lot of news. IPCC is going to be continuing to release its new assessment report called AR6. IPCC is, of course, the Intergovernmental Panel on Climate Change, which is under the United Nations Framework Convention on Climate Change, which puts together all the science and provides lots of details on climate science, physical causes, extremes, mitigation, adaptation, and so on and so forth. This is a very vast topic. In fact, I have a whole course on carbon cycle, including the evolution of carbon cycle and regulation of climate through Earth history on my other channel. But here, in this context of the introduction to climate science, climate change, and climate modeling, I'm going to stick mostly to the chapter in this book that we are using by Schmittner. Okay. So he starts with this figure of the carbon cycle. Numbers in the boxes represent reservoir mass. So we talked about the bucket and the inflow and outflow and balance and equilibrium and so on. So this is basically that idea that you have a reservoir size where a certain amount of a material, let's say CO2, exists, and there are fluxes coming in and fluxes going out. The important concept also that is relevant that I have used without explaining completely is the so-called residence time. I said several times that we worry about the concentration of the greenhouse gases, their global warming potential, and their residence time. So if you have a reservoir size here showing 589 petagrams carbon as a total, then the when it's in, if atmosphere was in equilibrium, you would take the flux and divide it by, take the reservoir size and divide it by the flux, because in equilibrium, the influx would be equal to the outflux. So you will get a residence time, which is the average time that particular material like carbon dioxide you are considering. Why is it important? It's a very useful chemical concept, chemistry concept. For example, let's say you are in a coastal region, a ship comes in and dumps a bunch of oil by mistake, then residence time would tell you on average how long it would take for the oil to get washed out if we did nothing. Or it was used in the 50s when bombs were being exploded in the atmosphere because we didn't know much about radiation effects. People would actually sit on the front line to watch nuclear testing. So the nuclear material radiation that is released purposefully at that time or accidentally by Chernobyl and Fukushima and so on, how long it would take for them to wash out. So it's a useful concept. If it is not in equilibrium, then the same concept is called characteristic response time. It's again the time over which the material that is added or accidentally released dies away exponentially, and how long that would take, and so on and so forth. So coming back to the carbon cycle, we are looking at the reservoir size of 589 petagrams. It also can be converted into gigatons. Carbon, you always have to be careful. Petagrams, gigatons, carbon, CO2 equivalent, so we keep using different things. There is a conversion factor of 3.7 between carbon and CO2, for example, because of molecular weight and so on. I will show another figure next, which shows that this number in the atmosphere keeps changing because we are constantly increasing the amount of carbon, CO2 in the atmosphere. But nonetheless, here we are looking at a flux of plus 240 plus minus 10 petagram carbon per year. So the average atmospheric increase is about 4 petagrams carbon per year. So each year you look at this, it's going to look different. And we've been talking about ppm, parts per million by volume of 420 or so right now, and the amount of carbon basically tends to be about twice that. So currently it would be about 800 petagrams. Okay, just make sure it's carbon and not CO2. Yeah, just make sure. Okay, so just look at the boxes, the numbers. The main thing to worry about is that you have large numbers going in and coming out. So let's say here we are looking at ocean atmosphere gas exchange. It is showing 80 petagram carbon per year going in, so 60 plus 20 anthropogenic. So all the red numbers here are anthropogenic fluxes, and there is 78.4 coming out. So anthropogenic there essentially is how the solubility of the CO2 in the ocean is changing, and how the ocean carbon chemistry is changing, and so on. But the main thing to note is that the net uptake or release of carbon by a reservoir is a difference between these two large numbers. So small amounts are being sequestered or released. So that's the same between the atmosphere and land, and so on. So you have to be careful that when we are looking for carbon sources and sinks, often there are small numbers, difference between two large numbers. So we have to be very careful in budgeting these things. So here is the net ocean flux, 2.3 plus minus 0.7. So there is a large band of uncertainty around it, because we are talking about global means and so on, and there is 0.7 coming out. So the black numbers are natural, and the red numbers are the anthropogenic. So just carry these multiple pieces of information in your head. Okay, so the surface ocean here has a reservoir of 900 petagrams with fluxes of 90 and 101 between the intermediate and deep sea. So in the deep sea there is 37,100 petagrams with flux of 155 plus minus 30. Ocean floor has ocean floor surface sediments are 1750 petagrams carbon. And there is an exchange between marine biota and surface ocean, where photosynthesis, respiration, a lot of life exists: phytoplankton, zooplankton, fish, large fish, birds, etc., etc. Of course, birds don't live in the ocean. So the exchange of 50 going into marine biota and 37 back out. So net biomass is about 3 petagram carbon there. So you are exporting 11 petagrams carbon to the intermediate and deep sea, and then there is some being converted into dissolved organic carbon, which we will see in a minute, and that is a big pool there with 700 petagrams, which is exchanging 2 petagrams carbon with the deep and intermediate ocean, and so on. So you can get a sense of the residence time here. You take any particular reservoir size of, let's say, 37,100 petagrams and divide it by one of the fluxes, and that gives you how long carbon stays in each of these boxes or reservoirs. Okay, that's the usefulness of residence time. Of course, we are taking out fossil fuel reserves in terms of gas, oil, and coal, and we are burning them at this rate of 365 plus minus 30. So that's there, and we are releasing various amounts. So there is burial happening, soil carbon, there is net land flux exchange, again 2 big numbers, 123 and 118.7, with natural and anthropogenic components of fluxes. So net land flux is 2.6, anthropogenic flux plus minus 1.2 going in, and natural uptake is at 1.7. And net land use change is releasing a 1.1 plus minus 0.8 to the atmosphere. Fossil fuels, including coal, oil, and gas, and cement production together are releasing 7.8 plus minus zero point 0.6 petagram carbon per year. Again, remember petagram carbon versus CO2. The numbers can be confusing unless you are tracking those carefully. So fresh water is outgassing 1 petagram carbon per year. There is weathering uptake at 0.3 and 0.1 respectively here from acidification of soil water and atmospheric CO2 dissolution, and volcanoes are releasing about 0.1 petagram carbon per year. Permafrost has 17 petagram carbon in its reservoir, and vegetation has 450 to 650. Uncertainty is quite large there with anthropogenic fluxes, deforestation, agriculture, etc. of minus 30 plus minus 4.5. Or it may be 45 there, so large uncertainty. Soils have a reservoir of 1500 to 2400 petagram carbon. So the units are petagram carbon per year, and stocks are in petagram carbon. Fluxes and stocks. Okay, so the fluxes here, just to be sure, are anthropogenic effects averaged over 2000 to 2009. I should have said that first. So it's not over the whole industrial period, and it's not per year. Typically the numbers don't come in very quickly, so we average over a certain period, like a decade here, to look at the fluxes to get a better handle on the averages. Okay. So this is the combination of natural and anthropogenic carbon cycle, or natural carbon cycle that is being perturbed by anthropogenic activities. Just to quickly look at how things change, this is for year 2014 or so, I think. So here the atmospheric reservoir already has 800 petagrams. Photosynthesis and so on. Again, the numbers differ depending on whether it is carbon or CO2. Typically it is carbon, so it is gigaton carbon per year here. So it is, instead of petagrams, they are doing gigaton carbon per year, so you have to be careful about that as well. And atmospheric carbon net annual increase again is 4 ppm per year, or 4 gigaton carbon per year. So averaged versus concentration, reservoir size versus concentration. Just make sure you understand all those things. The number here, fossil fuel, cement, and land use changes at 9 gigaton carbon per year. Okay, so the numbers in parentheses here refer to stored carbon pools that we are looking at like before. The main thing I wanted to point out is that the atmospheric reservoir size keeps changing, or amount of total carbon in the atmosphere and ppm keep changing, because we are constantly adding fossil fuel and other anthropogenic fluxes. Ocean also changes, but deep ocean changes much more slowly than the surface ocean, because surface ocean is exchanging fluxes. The same for soil carbon and so on. Of course, soil carbon also is perturbed by agriculture, deforestation, urbanization, and other land uses. Okay, so I want to leave this podcast here just to give you a sense of the kind of details one has to worry about when it comes to carbon cycle. And we haven't said anything about the time scales. Remember that these happen on very different time scales. Weathering is typically happening on geologic time scales. Ocean surface exchanges are happening on monthly, yearly time scale, whereas the surface ocean and intermediate deep oceans are happening on multiple years, decades to centuries, and land is happening much faster. Vegetation is growing on decadal, multi-decadal time scales. Fossil fuel burning is adding on a daily time scale, and so on and so forth. So we have to always be mindful of the various time scales that are involved as well.